Hello, folks. Welcome back. So, what we have been doing so far, we are studying the interaction between, or the relationship between the forces and the motion of particles. We looked at Newton's equation that was showing direct relationship between the forces and accelerations of a particle. And we saw how we could use this to make a lot of calculations and inferences. We considered a different framework, again based on same principle. It wasn't different, but packaged and formulated differently. It was the topic of energy and work, and we saw its value and power in solving many of the problems that we couldn't normally solve or easily solve with Newton's equations. It would give us the direct relationship between positions, velocities, and a notion of effort, forces along the way. It was the topic of the work. And that was great. Now we want to introduce a third way of formulating, again, the same principles. And that is the topic of impulse and momentum. Here we will see we can, instead of going from one location to another, that was the way we did it in work and energy, we see how we can go from one time to another. So the range is given as a time range instead of a location range. And we will use this to bypass some clunky integrations, some forces that maybe not easy to calculate. We'll see a lot of value in this new way of looking at the problems. So to begin, let me start with Newton's second law that we are already familiar with. Oops, where is it? Sum of forces equals mass times acceleration. And this is written in the inertia frame. If I want to expand it a little, I can write it as time derivative of the velocity. Instead of acceleration, I can write it's the same definition as a time derivative. Now let me do a bit of trickery, bring this dt to here. So I have excuse me. I have sum of forces times dt equals m dv. And now I have both sides with some differential term, and I can take integral of this. Sum of forces dt equals integral of m dv. Assuming that the mass is constant, let me continue writing this. Sum of forces dt equals m integral dv. And this integral is easy if you're taking the integral from some time t1 to t2, and this integral from the velocity at that time v1 to velocity at that other time v2. This becomes sum of forces. Let me see. I want to do something else too here. Integral of a sum of terms is equal to the sum of integral of individual terms. So I bring the summation out. Integral t1 to t2 f dt equals m. On this side I have v2 minus v1. And finally, let me see what is the best way to package this. And let me add one more line, t1 to t2 f dt equals mv2 minus mv1. All right, so I started from Newton's equations, just a bunch of rearranging things and taking integral. I arrived at this. What does that even mean? This is referred to as the principle of linear impulse and momentum. And it is a very fundamental principle. It becomes a lot more useful when you're talking about rigid body. Let's give these a bit of names. No, let's do this here. So let's define the integral of f dt. Call this I. This is linear impulse. So the time integral of force, let's call that a quantity called impulse. And let's call this term mv. Give it a name L. Call that linear momentum. And notice that, this is also a vector. If I want to write the same thing with this new notation, I have sum of all impulses equals change in L, change in linear momentum. Or another way I can write it is L1 plus sum of all impulses acting on a particle equals L2. What it means is that if I know how much impulse has been applied over some time range, has been applied to a particle, I can directly go and calculate how much its momentum changes, and momentum being related directly to the velocity and inertia, the mass of the particle. This principle of impulse and momentum gives us a very quick shorthand transition from velocities at initial and final time, given the possibly known amount of impulse. Something to note here is that we do not take the integral of accelerations as we used to do in the Newton's equation. We now take integral of force. We still do the integral, but it is applied to a different quantity, and changing that quantity, what is being integrated, actually gives us a lot of leverage in many problems, because we can in many ways calculate this impulse significantly more easily than calculating or integrating accelerations. In many problems we will see we don't even know exactly how forces work, but we know that the integral somehow turns out to be zero, and that would lead us to the total momentum of that particle should remain the same. It would not change. We will get to that in more detail in a bit. But let me add a few points here. Do I want to add a few points here or leave that? No, let's do it here. So this impulse, both of these, impulse and momentum. Both impulse and momentum are vector quantities. So it is important. We are back to vector domain. For a short while, we took a detour into scalar domain when we were talking about work and energy. But we are back to vectors. So mind that both the impulse and momentum, you have to consider the directions of these as well as their magnitude. Something very important to remember. The units for impulse is times second, because you're integrating force. Oh, what did I write? Time second, Newton second. Newton second, you're integrating force over time. And that you can see, it has Newton times dt second. And unit of momentum is kilogram meters per second, or their equivalent in the imperial system. What else? Yeah, one other thing. The magnitude is okay. We can easily find that. The direction of these quantities are directions are require a little bit of thinking. So for momentum, the direction is the same as the direction of velocity, as direction of velocity of particle. And that is because this mass is a scalar. So a scalar multiplied by a vector just changes the size of the vector, but does not change its direction. The direction of I, the impulse, linear impulse, you cannot immediately assume, because remember that you're summing over time a whole bunch of forces. So if the direction of the force, for instance, changes, you may end up with any possible direction. So in this example, progression of force over time is this. You should end up with a summation and a total impulse that is kind of upward. So you need to take into account both the magnitude and direction of force as it changes over time. All right, I think that is good enough for this video. We introduced the concept of impulse, concepts of momentum, and how these two concepts are related to each other. And the relationship is called the principle of impulse and momentum. I'll add a bunch of more informations and details in the next video, and yeah, let's take it from there. So I'll see you in the next video.